Well, before we get started on today, I know you all want to talk a little bit about exam 2, and I do too, and we'll get that out of the way and then we'll get started. And the first thing that I want to tell everybody is let it go, right? I mean, we're going to fix this. So it was a little lower than I'd hoped for, so what I'm going to do is I'm going to do a couple of workshops. You only have to come to one. It'll be next week. I'm typically here Monday evenings and Wednesday evenings, but I'll send out and we'll see what works. And so the way that this will work is you'll come, I will give you the exam again. And by giving you the exam again, I mean not literally handing you out a copy of the exam. And we will go through them one by one. We'll work on them together. We need to figure out where some of the issues might be in answering some of these questions. So basically what I'll do, we've got 26 questions. We'll start at question number 1. I'll have you spend 2 or 3 minutes working on it, and then I'll go to the board and we'll work on it together. And hopefully we can find places where the issue is. So it's completely voluntary. You don't have to do it. But I've decided that I'm going to give you 60% of your missed credit back for just attending and doing all the problems with me. You won't have to turn anything back in. You'll sign a sign-in sheet. And so what I'll do is I'll go back to my office and I'll look at everybody and I'll look at what the score you made, and I'll subtract that from 100, not 104, because the bonus doesn't count in this. And so let's say that's a difference of 30 points. I'll take that times 0.6, and that's what you'll get in workshop points. So it'll be a little more than half of your missed credit. How does that sound to everybody? Okay. You will have to work those problems, okay? It's not just coming in, sitting down, and listening to me. You'll have to work them. I'll expect you to engage. As you watch me work the problems, if there's something that's not catching, I'll depend on you to say, whoa, not understanding what's happening there, and then we can stop and do it. So it'll be an effort on your part. It'll be an effort on my part. But let's do some workshops, some problem solving together, and let's see if we can figure out where some of the problems are. My guess is that some of it is fairly minor stuff, but when you're dealing with a multiple choice test, it's either you got it or you didn't, right? So I think we'll be able to work on that. Does that sound good to everybody? Yeah? Fair enough? Okay. So the goal in this class, right, is to prepare you for biochem. That's my goal. I want you to go into biochem being prepared, so I'm not worried about your grades. You shouldn't be worried about it at this point. Let's work together and let's solve the problem. So today we're going to continue talking about chapter 9, but before we do that, last time we talked about aromaticity. What was aromaticity? Generally define that for me. What does it mean for something to be aromatic? I'm not talking about the 4 things yet, but just in general, what does it mean for something to be aromatic? Pardon? There is smell. That's one of the terms that we talked about. But not all aromatic compounds actually have much of an odor, right? You all know that from going to a restaurant and say, oh, that's a wonderful aroma, or that's a terrible aroma. That's a nice perfume you're wearing. That's a good aroma, right? And there are aromatic compounds and things that smell, but that's not what we're getting at here, right? An aromatic compound is something that is unusually stable. Right? It is more stable than we would have thought at first hand. Right? And so the example that I started off with, right, was benzene. And I said there are 3 double bonds. You might expect it to react with bromine and other things and add 3 times. And in fact, when I did the demonstration, right, and I added bromine to benzene, what happened? No reaction. But when I added it to cyclohexane, we got a reaction, right? We could tell that by the color. And so the benzene just sat there and looked at the bromine and nothing happened. That's because that benzene molecule is more stable than you would have predicted just looking at the double bond structure. And so there are 4 things that all aromatic compounds have to have in order to be aromatic. So let's and it doesn't matter what order, right? But what were they? Has to be cyclic, right? I start here, and I go all the way around without ever lifting my pin. It's a cycle, right? What's rule number 2?
Planar.
Yeah, planar. Has to be flat. Right? And benzene, I don't have my model kit out, but it was flat, right? It could lay down on the table, no problem. What's the third thing we have to have? Completely conjugated, right? It has to be has to have complete conjugation. And what does that mean practically? It means practically that every atom in the aromatic system has to have a p orbital. And each one of those carbon atoms is sp2 hybridized, which means it has a p orbital, right? So we've got to be cyclic, we've got to be planar, we've got to be completely conjugated, and we have to what? We have to satisfy Huckel's rule, which is what? 4n plus 2 must equal the number of pi electrons. That's right. And benzene does that, right? So it's got 6 pi electrons. So 4n plus 2 equals 6. N equal 1. And Huckel's rule states that the n has to be what? An integer. It has to be 0, 1, 2, 3, 4, whole number. Can't be a half or 3/4 or anything like that. It has to be a whole number, right? And so all of these things have to be in place for a system to be aromatic. And so looking at this, you know, and looking at the demonstration that we did last time, you might think, well, you can't do a whole lot with aromatic molecules. But in fact, they can undergo reaction. And that's what we're going to talk about today. They go through a reaction called electrophilic aromatic substitution that we chemists just abbreviate as EAS. So they undergo electrophilic aromatic substitution. What does that mean to you to hear those 3 words together? What does electrophilic mean? Wants electrons. Okay, so an electrophile wants electrons. Aromatic, we know what aromatic is, we just talked about it. And then substitution, what does that mean?
To replace one thing with another.
That's right. And so if I look at benzene, what do you think I'm going to replace for something else? You think I'm going to replace a carbon? Or I've only got carbon and hydrogen, right? You think I'm going to replace a carbon or am I going to replace a hydrogen? Probably a hydrogen. That's right. And so in these electrophilic aromatic substitution reactions, you're going to find that we can substitute one of the hydrogens for an electrophile. Okay? So that's what we're going to talk about today. And there are several electrophiles that do this. And we'll talk about each one of them briefly. The good news is that the electrophilic aromatic substitution reaction, regardless of the electrophile, it's the same mechanism. You just have to know what electrophile you're dealing with. And so we'll talk about that. So here's the example, right? I've got benzene. I'm going to react it with an electrophile, and I'm going to replace one of the hydrogens for an electrophile. That's electrophilic aromatic substitution, right? And according to the demonstration we did last time, right? And just imagine that X is bromine here. So when we take benzene, react it with bromine, this doesn't happen, right? This doesn't happen. But notice the product. Is the product aromatic in that top reaction? I mean, it says it, right? What does it say? It is not aromatic. Why is it not aromatic? Well, it's certainly not planar. You wouldn't know that from the picture, but if you built the model, you would say it's not planar. What were you saying?
Same thing.
Yep, so it's not planar. It does have some double bonds, and it is cyclic, but it's not completely conjugated around the cycle, right? There's not a p orbital on those 2 carbons anymore. So do you think the product is more stable or less stable than the starting material? less stable, which means here's the starting material, the benzene, here's the product. It doesn't seem like that should happen, right? Most things don't like to sit on top of the hill. They like to get more stable. But, so the addition kind of chemistry that we think of with double bonds doesn't work here. You're right, we're going to get more sigma bonds, and I told you before that addition reactions lie to the right because we get more sigma bonds, but aromaticity is so much more stable than sigma bonds, right? So even though I'm getting some stability from some extra sigma bonds here, I don't have an aromatic product anymore, and so this is still way uphill. However, down here in the substitution reaction, I start with an aromatic compound, and my product is an aromatic compound. So that's why these reactions will work, because we end up with a product that is also aromatic, okay? Now, the best that I can tell you right now is you're going to have to memorize these 1, 2, 3, 4, 5 reactions. You're going to have to know them, okay? We can replace the hydrogen with a halogen. We can replace the hydrogen with a nitro group, NO2. We can replace the hydrogen with an SO3H, okay, a sulfonic acid group. We can replace the hydrogen with a carbon atom. And we can replace the hydrogen with a ketone. Okay? We can do all of these things through electrophilic aromatic substitution. What you notice is that the electrophile is different in each case. At the top, the electrophile is chlorine or bromine plus. You think I can buy a bottle of chlorine plus? I can't. I have to make it, right? And there's a way that we do it. Notice what is over the arrow. I need the halogen, X2, I need bromine or chlorine, and I need an iron salt. Okay? So I can use iron trichloride or I can use iron tribromide. We'll talk about how that works. But that's what is necessary to replace the hydrogen with a halogen group. Notice what halogens aren't there. What halogens aren't there? Fluorine and iodine. Yeah, we can't do that with this particular chemistry, okay? This is really limited to chlorine and bromine. I can replace the hydrogen with the nitro group. I need NO2 plus, and I can make that by a mixture of nitric acid and sulfuric acid. Anytime you want to put an NO2 group on a benzene ring, you're going to need nitric acid and sulfuric acid to do that. It's nasty stuff, but it works. It makes NO2 plus. If I want to replace the hydrogen with a sulfonic acid, I need SO3H plus, and I'm going to do that with SO3 and sulfuric acid. Again, a nasty concoction of stuff. I can replace the hydrogen with a carbon by using alkyl halides. Typically, this is using alkyl chlorides, but alkyl bromides will also work. And we use aluminum trichloride to make that reaction go. What is the electrophile? What is R plus? What's another name for R plus? Boy, hangman. Say it. Carbocation, that's right. What do we know about carbocations? And they like to rearrange. Oh my gosh. So this so-called Friedel-Crafts alkylation reaction, the tough part about it is you got to think, oh, will it rearrange to something more stable? Okay, that cardinal rule of carbocations will come into play. And then there's this other reaction called Friedel-Crafts acylation, which replaces the hydrogen with and makes it a ketone. Okay, so you need to make a note card of these reactions, and you need to know all of the reagents that make this work. Okay, you got to commit this to memory, or it will be difficult on the next exam. Trust me. Okay. Let's talk about the general reaction mechanism. And we're going to pick on benzene. And we're just going to imagine that we have an electrophile, a generic electrophile. Okay? So I've got benzene and I'm gonna react it with a generic electrophile. Now, do you all think I can have a bottle of just E plus? No. What do we know about our charges? They have to balance out to zero, right? So if I've got E plus, I've got to have some other counter ion, and I'm just going to call that A minus. So let's just assume we've got both, okay? Again, this is generic, okay? What do you think happens in the first step? You all told me that an electrophile wants electrons. You are absolutely correct. Where can it get electrons? Where are the electrons at that are reactive?
The hydrogen.
Hydrogen does have electrons between the carbon and the hydrogen, but that's a sigma bond. That's hard to get to. Now, we are going to substitute the E for the H. I think that's where you were thinking, right? But are those the more reactive electrons, sigma or pi? Pi electrons are the more reactive. And why is that? They're easier to break. That's true. And they're also not between two atoms. They're above and below the atoms, right? They're in those p orbitals. So yeah, it's going to react with one of these double bonds, okay? So I've got electrons. I want electrons. That's what happens in the first step. Okay, and so I'm going to draw out the hydrogen that's on that one, E, and then that double bond is still there, that double bond is still there, there's still a hydrogen here, I'm going to draw that, there's hydrogens on the other ones, you all know that, right? So what else is here now? If these electrons reached out and grabbed the E plus, what happened to this carbon? Right now I've only got three things attached to it, right? So what has to be on that carbon? If something that is neutral reacts with something that is positive, what does the charge have to be? It has to be positive, right? This is a carbocation. And then, of course, A minus is still out here, right? Think about it. I took these electrons, both of them, from the bond and made a bond to E plus. That means I took an electron from this carbon, which was neutral, so now it's got to be positively charged. Right, if I circle that carbon atom, carbon comes in with 4. It formally has 3. 4 minus 3 is plus 1, right? So that's why we have the positive charge, okay? Is that aromatic? It is not. Can I get it to be aromatic pretty easily? What do I have to do? What do I have to do to make this aromatic again? I need a new pi bond, right? I need to put a pi bond between here and here. How can I do that? I got to lose this hydrogen, don't I? And these electrons got to come in here somehow, right? Well, what happens is my counter ion just reacts. Those electrons go there. That's all there is to this mechanism in terms of the electrophilic aromatic substitution. Okay? It's just this step followed by that step. So the trick is going to be remembering how to make E plus. Right? If I want to make Cl plus, I know I'm going to need Cl2 and iron trichloride. If I want to make Br plus, I need Br2 and FeBr3. Okay, that's going to be the thing that you're going to have to focus on. This is the general reaction mechanism, and it's a pretty straightforward mechanism. Okay? But this is what aromatic compounds like to do. They like to do electrophilic aromatic substitution. I started with an aromatic compound. I went through a non-aromatic intermediate, and I got an aromatic compound. Okay? You can detect this. You can't put it in a bottle. It will immediately do this and give you the final product because the aromatic system is more stable. Okay? This is what it looks like if you draw it out in a reaction energy diagram. What does that kind of look like? What other substitution reaction have we looked at in the past that had a diagram that looked almost identical to that? SN1, yes. This looks like an SN1 reaction. So which one of the steps is the slowest step? This step or this step?
The first one.
The first one is the slowest step? Why is that? Well, looking at the diagram, we can tell that that's the highest energy, right? Starting here, going there, it takes the most energy. That's a true statement, but that's just reading a graph. What's the reason behind it? The reason behind it is because I'm going from an aromatic compound to a non-aromatic compound. I'm going from something that is more stable to something that is less stable. Okay? The second step occurs really quickly. The energy of activation is very low, and I'm going from something that is non-aromatic to something that is aromatic. Okay? So this is the general reaction mechanism shown as an energy diagram for you. Looks very similar to the SN1 reaction that you learned earlier. Okay? So we can do halogenation, right? We can take benzene, we can react it with chlorine in the presence of iron trichloride, and we get chlorobenzene. We can take benzene, we can take bromine and iron tribromide, and we can get bromobenzene. So the demonstration that I did the other day where I had benzene and I put a few drops of bromine in there and it stayed colorless, that was because I had no iron tribromide in there. What do you think would have happened if I had just thrown in just a little bit of iron tribromide? What do you think would have happened to the color? It would have dissipated. The reaction would have happened and I would have ended up making some bromobenzene. Okay? And so, could I do that demonstration? Yes, but I'm not going to because it makes HBr gas as a byproduct. That would generate HA. Hydrogen bromide gas is not very healthy for us, so I'm not going to do that in this room. Okay, but we could have done that pretty easily. Okay? So, let's think about the general reaction mechanism again, but this time let's be specific. And instead of calling it E+, let's use the real set of reaction conditions. So let's suppose Rose comes in and says, I need to have some bromobenzene. And so she throws these things together so that she can make her bromobenzene. We know that that's going to happen. So let's just go ahead and draw a product. And let's think about what happens. Somehow I've got to generate Br+, don't I? What do we know about bromine? When we look at the periodic table, what do we know about its family? Do you think bromine would like to be positively charged? I'm seeing everybody shake their head no, and that's the right answer, but can you tell me why?
The very much negative.
Yeah, the halogen family tends to want to attract electrons to itself. It typically doesn't want to be positively charged, it typically wants to be negatively charged, right? Think about all the things you learned in Gen Chem about salts, iron bromide, sodium bromide. It's always Br minus, Br minus, Br minus, or Cl minus, Cl minus, Cl minus. Halogens like to take electrons, they don't like to give them away. So somehow we got to trick bromine into being positively charged. What do you think is going to do that trick? It's going to be the iron tribromide, right? Okay. And it turns out that iron tribromide is a Lewis acid. What does that mean? What is a Lewis acid? It accepts an electron pair, right? A pair of electrons. Where can I get a pair of electrons from bromine? What am I not drawing on bromine? Well, I know that bromine has a bond, right? Do you think it's going to get a pair of electrons from between these two bromines? Probably not. It's kind of crowded, right? But what's around bromine that I didn't draw? Lone pairs. So that makes bromine what? Oddly enough. If this is a Lewis acid, this can also function as a Lewis base. That's exactly what happens. And so this will react with the iron tribromaide, give me Br, FeBr3. And if I take something that's neutral and I give it a pair of electrons, what's the charge on this? If I take something that's zero charge and I give it an electron, what's its charge now? Negative. So iron tribromide becomes this compound now, and iron gets on negative charge. What do you think about this bromine now? If I circle that, bromine comes in with how many? Comes in with 7, right? I circle it, it's got 1, 2, 3, 4, 5, 6. What's its charge now? Positive 1. What did I just do? I just made bromine positive. I've got my Br plus. Okay? That's how we generate Br plus. Okay? Does that make sense to everybody? Lewis acid, Lewis base chemistry. I get this complex. That looks kind of weird though, doesn't it? Right? So let's think about that now. So let me just draw that up here. So we've got Br plus FeBr3 minus. So how would I draw my arrow from the benzene ring?
You draw it to your, you draw it to your BR plus.
Yeah, you would think I would just draw it to the Br plus, right? I got electrons in the ring, I've got Br plus. He told me I needed Br plus, right? You made an absolutely correct guess that just happens to be wrong, right? And why is it wrong? It's wrong because this bromine is sandwiched in between two other things, right? But it still makes this bromine kind of plus because it's pulling electrons to itself, right? So the reaction is just like that. So it's actually the end bromine that ends up getting added. Okay? And so you get this. Just like we did before. Okay, so there's the bromine plus FeBr4 minus. Does that make sense? So now my FeBr4 minus removes the hydrogen, and I make my product, plus I get HBr, and I get my FeBr3 back. Okay? Now, I don't want to go through the mechanism of how that happens with you. Just know that that happens. Okay? So what does this mean about iron tribromide then? If I need iron tribromide here, but I get it back, do I need a lot of it? It's catalytic. I just need a little bit. Okay? And in fact, the cool thing about this reaction, and don't worry about writing this down, I'm just excited to be able to tell you about it. Okay? But I won't examine you on this. You actually really don't even need iron tribromide. You just need a little iron. You can take a little bit of iron and put in the reaction. It will react with the bromine and make its own iron tribromide, and the reaction goes really well. When I used to do this reaction, you can literally go to Lowe's and buy some nails, and cut the nails up because they're all made of iron, and you can just throw a little piece of that in there and the reaction goes wonderfully. Okay? Cheap, easy to do. Okay? But it makes the iron tribromide by putting iron in with bromine. So a lot of times people don't even buy a bottle of iron tribromide to do this. But this is the mechanism for the halogenation. It's this halogen that's the plus, even though this one formally is positively charged. Okay? So these electrons come in, react with this bromine, those electrons go to the positively charged bromine, and that's how the reaction works. Exactly the same if we're talking about chlorine. It's the end chlorine that works for this. Okay. Well, why is this important for us? Turns out that putting halogens, especially chlorines, on molecules has turned out to be important, both today and historically, both for good reasons and bad reasons. For example, if you look at Wellbutrin or Zyban, this is a very potent antidepressant. It's also used in smoking cessation for people who want to stop smoking. It helps reduce nicotine cravings. You'll see there's an aromatic ring with a halogen on it. That halogen happens to be chlorine. If that chlorine is not there, it doesn't work as a drug. You have to have that halogen there. How do you think they got that halogen on there? Electrophilic aromatic substitution. You cannot go to crude oil and get chlorobenzene or bromobenzene. That's completely a person-made thing. Okay? But, this is a big drug. I mean, people use it. It helps a lot of people in a variety of ways. You can also look at chlorpheniramine, right? This is an antihistamine this time of year. Many of us are probably taking the generic version of this because we're having allergy attacks, right? And so we might be taking this. But you'll see the aromatic ring has a chlorine on it. You take that chlorine off, it doesn't work anymore. You got to have that halogen there for it to have the biological activity. Okay, so two good reasons why we need to be able to put halogens on aromatic rings. Here is kind of a bad reason, right? For those of you who know anything about the Vietnam War, you probably have heard about the fact that our service members came back with Agent Orange exposure. That created all kinds of terrible side effects. Agent Orange is this mixture of compounds. They're herbicides. And the reason that we used it in Vietnam was it was jungle warfare, right? And it's hard to see the enemy in a jungle. So what they would do before a battle, maybe even during a battle, is they would come through and they would spray Agent Orange over the battlefield to defoliate the forest. Not a good idea in general, okay? I'm not defending what was done, okay? It's not what I'm saying. But the chlorines had to be on there for this to work as defoliating agent, okay? And so, but it also creates all sorts of medical issues. If you go look at some of the current herbicides that you probably use in your own yard, they are derivatives of Agent Orange. They're not Agent Orange, but they have an aromatic ring, they have this acetic acid component to them, and they have halogens just in different places. Okay?
So was this reaction repeated multiple times to get the several
Yes.
lines in it?
It was. So you can actually, you can do more than one substitution. You just have to use more chlorine and more catalyst. Yeah. And from my understanding, I've never studied this completely. You can see it's a mixture of what they call 2,4-D and 2,4,5-T. It's a mixture because the reaction doesn't go to completion and give you all three chlorines. It'll do it some, but it kind of stops and gives you this mixture. But it turned out, beneficially to this, that mixture turns out to be a very potent herbicide for some reason. I'm not a herbologist or whatever we call those folks, so I don't really know the mechanism of that. But very potent defoliating agent. All right, we can also put nitro groups on. Okay, and this is very important. So we can replace the hydrogen with a nitro group, an NO2, so we can go from benzene to nitrobenzene. Turns out this is an important reaction because you can take that and you can make aniline, Okay, so what we're making here right now is a carbon-nitrogen bond in the electrophilic aromatic substitution reaction. And that turns out to be particularly useful, okay? So for example, what might you all think about when you hear the word nitro? What do you think about when you hear the word nitro? Think of nitrogen, of course, yes. You might go to Starbucks and think about getting the nitro brew coffees. That's not what we're talking about here, although it is related. What else do you might think about? Liquid nitrogen? Did you say what? Cars?
Yeah.
What about cars?
In car movies, that's what they use to get fast.
Yeah, they use nitrous, right? They use nitrous, so it's something that gives a lot of energy, right? Nitrating aromatic rings is very useful in making a compound called TNT. Anybody know what that is? What is it? Explosive. That's right, it's an explosive. A very powerful explosive, right? Does anybody know what it stands for?
No
Trinitrotoluene. You put the 3 nitro groups on there using electrophilic aromatic substitution. But instead of starting with benzene, you start with toluene. So you take toluene, which is some used in paint thinners and fingernail polish removers. You take nitric acid and sulfuric acid, you mix it together, and you can make trinitrotoluene. Putting the first nitro group on is no problem. Putting the second nitro group on is a little harder, but still not much of a problem. Putting the third nitro group on is difficult, and you'll probably kill yourself and blow yourself up doing it. Okay? We made a lot of TNT during World War II. There are places in the United States where the soil is considered explosive from back in World War II. We were fighting a war. Do you think they were worried about the environment? They were making TNT and they were throwing the waste out, literally outside the back, into the ground. And that had residual TNT in it. There are places in America where you can go where they say that soil is potentially explosive. Okay? It's actually fairly stable because it's mixed with the soil. But there's enough TNT in the soil that you could extract it and you could blow yourself up.
Slightly off topic, but wouldn't that just degrade the nitroglycerin to that end?
Pardon?
Wouldn't that just degrade the nitroglycerin to that end?
Would that degrade to nitroglycerin? Nitroglycerin is a different compound altogether. It is, so glycerin you get from making soap. And you put nitro groups on the alcohols, actually. So it's a very different compound, but it is an explosive. So anyway, we no longer manufacture TNT in the United States, interestingly enough. It's all imported from somewhere, I don't know exactly where. Also, this sulfonation, these sulfonic acids are useful in soap, or, well, let me rephrase that, in detergents. A lot of detergents need that sulfonic acid group. So you use artificial detergents to clean your clothes. Some of them are made by this sulfonation reaction of benzene and benzene derivatives. So the trick is, right, how do we make NO2+? Well, this is how you make NO2+. This is the mechanism. I'm not going to go through it in great detail on the board with you. But what's odd about that? What did you all learn in general chemistry about nitric acid and sulfuric acid? They're acids, and they're what kind of acid? Strong or weak? They are strong acids, okay? But if you look at it, right, nitric acid here is donating a pair of electrons to the hydrogen of sulfuric acid. So what does that mean nitric acid is behaving as here? A base. That's odd to think about, right? But it's relative. So the nitric acid donates a pair of electrons, picks up the proton. You end up with this molecule that looks like an oxonium ion that we learned about in the alcohol chapter, right? And the water can just leave. And when that happens, you get NO2+. That's how you make NO2+. You just mix nitric and sulfuric acids together, and you can get that, okay? Very easy reaction to do. I did this reaction countless numbers of times in my PhD work. I made nitro compounds, a molecule called cyclophane, which is two benzene rings stacked on top of one another, held on top of one another by a bridge. And we would nitrate it and then do other things with it. We don't need to go into that. The cool thing about that is that these two benzene rings were so close together that they actually talked to one another. I could do something to one ring and the other ring would know that it happened. That's kind of weird to think about, that molecules can know what's going on, but it happens. I'm not trying to imply that it was living, it's not, right? But I mean, when I messed with one ring, the other ring knew that something happened, and that was kind of cool, and that's what we were studying, okay? The same thing with SO3H+, the sulfur trioxide, which is a gas, is bubbled through sulfuric acid, and the SO3 picks up one of the protons, and it becomes SO3H, and sulfur has a positive charge on it. So that's how you generate that electrophile, okay? So if I want to put an SO3H on a benzene ring, I just need to bubble bubble SO3 through sulfuric acid to make the electrophile for that to happen, okay? Friedel-Crafts is another named reaction. What named reactions have we learned so far? If you don't remember, that's fine, because I told you really didn't need to remember, but anybody remember? We learned about the Williamson ether synthesis. Remember that one? And so we've learned about that named reaction. Here's another named reaction that chemists just throw around, and it's called the Friedel-Crafts alkylation reaction. What we're doing is we're putting an alkyl group on benzene. Okay, so examples would be taking benzene, reacting it with this alkyl chloride and aluminum trichloride. How would I name that alkyl halide? What is that? What is that one? Ethyl chloride would be a common way to name it. There's nothing wrong with that, but how would we focused on just calling it chloroethane, right? So both names would be right. And when this reaction happens, I get that ethyl group put on benzene. So now I have ethyl benzene. I've put an alkyl group on it. The important thing here is I made a carbon-carbon bond. In biology and in chemistry, the most difficult thing in the world to do is to make a carbon-carbon bond. It is what every chemist really studies, or every organic chemist really studies. Every polymer chemist studies this, right? How do you make a carbon-carbon bond to make something bigger? How do you make a carbon-carbon bond to put something where you want it, right? This is tough, and there's only, if you break it down, about 5 to 10 ways to do this. And people have won Nobel Prizes figuring this out. People have spent their entire careers figuring out how to make carbon-carbon bonds. It's the tough thing. Crude oil only gives us so many molecules, and we have to put those together, usually through carbon-carbon bonds, to get the medicines that we want, to get the polymers that we want, to get everything else that we want, right? And so this is a tough thing to do, except you all can go into the lab and do it right now, doing Friedel-Crafts alkylation, okay? So, what's the electrophile here? The R group. Really, really close. What else do I need? Just R? R plus, right? It's a carbocation, right? I'm going to generate a carbocation from this. And it works pretty well. Aluminum trichloride is also a Lewis acid. Chloroethane, the chlorine has electron pairs around it. That's what happens first. Chlorine doesn't like to be positively charged. It's really close to fluorine, and it will actually break the carbon-chlorine bond and give me a carbocation. And wait a second, that's a primary carbocation. I thought those were unstable. They are. They react very, very quickly, but it does form. Okay? Can that rearrange to a more stable carbocation? No. It can't. If it rearranges, you still get the same thing. But that's what happens in this particular case. Okay? So you end up with a carbocation. So they're showing you a couple different examples there. We can also replace the hydrogen and make a ketone. In this case, they call it an acyl group. Don't worry too much about that. But we're going to use what's called an acid chloride. Instead of an alkyl chloride, we're going to use an acid chloride. Why is it called an acid chloride? Because that looks like a carboxylic acid that doesn't have its OH. The OH has been replaced with chlorine. Okay? They're easy to make, they're easy to use, we're not going to talk about that. Okay? But all I got to do is take the acid chloride, mix that with aluminum trichloride, and I get this. There's my electrophile. That electrophile will do the general mechanism and it'll make a carbon-carbon bond. But in this case, instead of just making an alkyl group, it makes a ketone, which is kind of useful. You can do that pretty easily. Okay? Works very well. This is called the Friedel-Crafts acylation reaction when you react with an acid chloride. Okay? Let's skip that for today. There are a couple of things that you need to know that won't work in this reaction. You cannot use vinyl halides. Notice that the chlorine is on an sp2 hybridized carbon. These don't do Friedel-Crafts alkylations. Chlorobenzene doesn't do this reaction. You've got to have the chlorine on an sp3 hybridized carbon for this to work. Okay? Not on sp2 hybridized carbons. So that's one limitation to the Friedel-Crafts alkylation, right? I can only react this with sp3 hybridized carbons. So that is one limitation. Okay? Here's an example that I want you all to take about 5 minutes, work with your partners, and I want you to explain to me, after you look at it, what's happening in both of those reactions. So take a moment, get the group, work through those two mechanisms on your own. So explain to me in words what's going on in the first case.
Seems like the aluminum is reacting with the chlorine attached to the carbon. And you're having your pi bond break.
Okay.
The lone hydrogen attaches to the CH to become CH2. You have a carbocation that attaches to the benzene.
Okay. So I've got my chlorine, right? And I'm going to react that with aluminum trichloride, which is what I think you were alluding to, right? And so what happens, and the way that you can think of this, right, is that I get this. Right? And chlorine doesn't like to be positively charged. I think we all can agree with that because it's so close to fluorine. And so it breaks the chlorine-carbon bond. And I get AlCl4 minus plus a carbocation. What kind of carbocation is that? Is that primary, secondary, or tertiary? It is secondary. It is a secondary carbocation. And I know that secondary carbocations can rearrange. Well, it just so happens that I have a hydrogen over here that if it moves, would give me a tertiary carbocation. So what happens is this hydrogen moves over through a rearrangement, and I get that carbocation, which is tertiary. Is that more stable? Is a tertiary more stable than a secondary? Yes, it is. So it does it. And it's that tertiary carbocation, that carbon right there, that adds to the benzene to make that carbon-carbon bond. So even though the halogen was on this secondary carbon that they've marked red, notice it's not the red carbon that's bound to the benzene ring. Okay? The same thing is happening here. When the chlorine leaves, right, through this mechanism that we've talked about, I have a primary carbocation. I have a hydrogen here that could shift and would give me a secondary carbocation. Is a secondary carbocation more stable than a primary? Yes, it is. And so it does it. Okay? So that's the thing that you're going to have to pay very close attention to on the next exam. If we're doing Friedel-Crafts alkylation reactions, rearrangements can occur. For the purposes of this exam, I will limit the Friedel-Crafts alkylation to the reactions of alkyl halides with aluminum trichloride. So you don't have to study as much stuff. But the book does talk about the fact that any carbocation, no matter how it's generated, can actually be used to make carbon-carbon bonds through the Friedel-Crafts alkylation reaction. So here's an example of where they take an alkene and react it with sulfuric acid. You get a carbocation. That carbocation can then do Friedel-Crafts alkylation reactions. So alkenes can actually do this. You can take an alcohol. Here's an example where they took terbutanol, right? You can react it. That leaves, you get a tertiary carbocation. Alcohols can also be used to do Friedel-Crafts alkylation reactions. Okay? The point is, it doesn't matter how you get to the carbocation. The carbocation is what's really doing the Friedel-Crafts chemistry. Okay? But for the purposes of our exam, we're going to limit it to the traditional, what we call Friedel-Crafts alkylation reaction and acylation reactions. Okay? So we're going to be dealing with aluminum trichloride and alkyl halides. Okay? So we can skip that. Why is this important? Well, here's some examples. Right? So this molecule is pretty easy to come by. You react that acid chloride with aluminum trichloride and you make a new carbon-carbon bond that happens to be a ketone. You've made another ring in doing that. Okay? And what you've done is you've made this important six-membered ring that, through several steps that we won't talk about, actually makes LSD. Okay? So this is how they actually make LSD. you probably think of LSD as a illicit drug that's on the street, and that's true, it is. But LSD actually is useful as a veterinary medicine. It's a tranquilizer, I think, for that kind of stuff. So while we don't typically think of needing to make it, there are legitimate reasons to make something like LSD, and it's this reaction that is very, very important in making that carbon-carbon bond for the rest of the structure. Okay, we won't talk about all the other reactions that have to go into place, but there's quite a few. Okay. All right, so you know what? I'm overlooking. So what we're gonna do is I'm gonna give you your quiz, tell you which problem to turn in. We're gonna give you a little bit of a break today, okay? We'll come back on Thursday and we'll pick up on this plus get into the next chapter, okay? But I want you to read ahead on substituted benzenes. Everything that we've been talking about so far has just been benzene, doing Friedel-Crafts chemistry and electrophilic aromatic substitution. It gets a little more complicated when you already have something on benzene. So I want you to read ahead on that. Okay, so read ahead on that really well before we come into class on Thursday. Okay? So I would like for you all to turn in problem 8.18, 818. For today's quiz. When you have that, just put it up there at the front, turn it in. I will see you all on Thursday. Enjoy the extra 15 minutes of your life.